Hey everyone, and welcome. When we talk about AI, it's easy to picture this one giant, super smart brain, right? But the reality is so much cooler. Machines actually have different ways of learning, almost like they have different kinds of minds. And today, we're going to dive into three of the big ones. So, you ever wonder how an AI can look at a mountain of data and suddenly discover brand new groups of customers? Or how it builds a predictor that's just scary accurate? Or even masters a game all by itself? Well, it's not some kind of magic trick. It all comes down to how it learns. And that's what we're getting into. Okay, so first up, let's imagine an AI that gets zero help. No teacher, no answer key, nothing. We just throw it into this massive sea of data and give it one simple instruction. Go find the interesting groups. This is the wild world of unsupervised learning, and its go-to tool is something called clustering. The key phrase here, and what I think is so fascinating, is learning by observation. Think about it. Most of the time, we think about training an AI by telling it what's right and what's wrong. Not here. Clustering is all about the machine just looking. It sifts through everything and starts finding things that are naturally similar to each other, forming groups on its own with no hints from us about what those groups should even be. And believe me, this isn't just some academic concept. Clustering is running behind the scenes in so many things we use every day. Marketers use it to find these little niche customer groups they never would have thought of. Scientists use it to map out land use from satellite photos. And get this, it's even used to spot fraud. How? By noticing a transaction that just doesn't fit in with any of your normal spending patterns. It's a total outlier. Okay, so how does a machine actually pull this off? Well, there are two main strategies. I like to think of it like organizing a super messy room. You've got two choices, right? You can either decide ahead of time, I'm going to use exactly 5 boxes. Or you can start building a kind of family tree of stuff where similar things are grouped together. So that first strategy is called partitioning. And it's pretty much what it sounds like. You tell the algorithm up front exactly how many boxes or clusters you want. It's like saying, hey, look at all my customers and sort them into, say, 3 main groups for me. Simple as that. Now, the most famous way to do this is an algorithm called k-means. Here's how it works. It starts by just randomly dropping k center points into your data, let's say 3 of them. Then, for every single data point, it asks, which center are you closest to, and assigns it to that group. Step 2, it looks at these new groups and recalculates the dead center of each one. And that's the loop. It just keeps repeating that process. Assign to the nearest center, update the center's location. Assign, update over and over again until the groups settle down and the centers stop moving. Pretty clever, right? All right, but what if you don't know how many groups you're looking for? That's where the second strategy comes in, and it's a totally different beast. This is hierarchical clustering. Instead of forcing your data into a set number of boxes, it builds this beautiful, intricate structure, almost like a family tree, that shows how every single data point relates to every other one. And that's the real game changer here. You don't have to decide the number of clusters beforehand. A common way it works is from the bottom up. It starts by treating every single data point as its own tiny cluster. Then it finds the 2 closest clusters and merges them. Then it finds the next 2 closest and merges them. It keeps doing this step by step until everything is one giant cluster. The output is this awesome tree diagram, and you can literally look at it and decide where it makes the most sense to snip the branches to get your final groups. So let's boil it down. Partitioning gives you 1 single answer, here are your K groups. Done. Hierarchical, on the other hand, gives you the whole map. It shows you the entire relationship structure, from the tiniest details all the way up to the big picture. Okay, so when would you use one over the other? It really comes down to trade-offs. The big win for hierarchical is that flexibility, right? You don't have to know the number of clusters in advance, which is amazing when you're just exploring your data. Partitional makes you lock that number in from the start. So here's the bottom line. If you know your target number of groups and they're pretty straightforward, partitional is your fast, efficient choice. But if you're on a discovery mission and have no idea what's in your data, hierarchical is going to give you a much, much richer story. All right, so clustering is awesome for finding patterns that are already there. But what if your goal is different? What if you need to build a crazy accurate prediction model? What happens when one model just isn't cutting it? Well, for that, you need a totally different mindset. It's time to bring in a team. And that leads us to our second way machines learn, ensemble learning. And this quote just nails the whole idea. You take a bunch of pretty simple models, we call them weak learners, that might not be all that impressive on their own, but when you get them to work together, they can form one incredibly powerful, strong learner. It's basically the wisdom of the crowd, but for algorithms. And you guessed it, just like with clustering, there are different ways to make this teamwork happen. The two big ones you'll always hear about are bagging and boosting. Think of them as two different management styles. One is all about democracy and working in parallel, and the other is about learning from your mistakes in a sequence. Let's talk bagging first. Here's the deal. You take your main data set and create a bunch of smaller, random samples of it. Then you train a completely separate model on each one of those little samples, all at the same time. When it's time to make a prediction, you just let them all vote. If most of your models say the answer is apple, then your final answer is apple. It's pure democracy, and it works because the mistakes of one model tend to get canceled out by the others. Boosting, on the other hand, is a whole different ballgame. It's not about parallel work, it's sequential. It's about learning from mistakes. You start by training one simple model. Then you look very carefully at where it messed up. The data points it got wrong, you give them more weight, making them more important. Now you train a second model, and its main job is to fix the errors the first one made. And you keep doing this, model after model, with each new one in the chain focusing on the toughest cases that the previous models couldn't crack. Okay, so we've seen how machines can learn by observation and by teamwork, but both of those rely on having a big data set to start with. What if a machine could learn with nothing but a goal and the ability to interact with the world? This brings us to the third mind of the machine, one that learns from pure trial and error, from experience. Welcome to the world of reinforcement learning. So here's the setup. You have an agent. This could be an AI playing chess or a robot trying to walk, and it's in an environment. The agent gets to try stuff, to take actions. When it does something good, it gets a reward, like a point. When it does something bad, maybe it gets a penalty. And over millions and millions of tries, it starts to figure out a strategy, a policy, that tells it what actions to take in any situation to get the most possible rewards in the long run. One of the most popular ways to do this is with an algorithm called Q-learning. And that Q in the name, it literally just stands for quality. As in, what's the quality or the value of taking a certain action from a certain spot? So the agent's goal is to build something called a Q-table. You can think of this as its ultimate cheat sheet for the game. This table keeps track of the score, the expected future reward, for every single action it can take from every single state it can be in. At the very beginning, this table is just full of zeros. The agent knows nothing. But every time it tries something, it updates the table with what it learned. So eventually, it discovers that going right when you're near the goal gives you a massive plus 100 reward, but going up from there leads to a penalty. Over time, this cheat sheet becomes a perfect roadmap for winning. All right, so let's pull this all together. We've looked at 3 totally different ways that a machine can think. First, there's clustering, which is all about learning by observation, just finding the natural patterns in stuff. Then we have ensemble learning, which is learning through teamwork, combining a bunch of simple models to make one super strong one. And finally, reinforcement learning, which is all about learning from experience, from trial, error, and rewards. Each one of these minds is incredibly powerful in its own right, each one designed to solve a totally different kind of problem. And that leaves us with a really big question, doesn't it? As AI keeps getting more and more advanced, will the future belong to machines that are masters of observation, or collaboration, or experience, or, and this is the exciting part, will the next leap in intelligence come from machines that can finally blend all 3?